Hello, my name is Elvina, and we prepared this talk together with my colleagues George. So, bolted Clang, how good is it on AArch64? Questions we wanted to investigate in this talk. What performance improvement can we obtain by using Bolt on AArch64 platforms? Should we bolt our Clang build? By our, here I mean our upstream version of Clang. And can we do better and change build process? During this talk, we will show performance results for timed compilation of LVM and CTMark from LVM test suite, patterns for Clang 18, 19, and 20, and show experiments with more and different profiles. So our story began with a goal of creating a fast compiler, a compiler which can do the same amount of work in a less time. Firstly, we did experiments only for Clang 18 and 19, but when the latest release of Clang 20 came, so we added it to our measurements. Let's look in the graph. Blue line here means original stage 1 Clang build, and orange line means Clang build which is optimized by LTO-PGO-BOLT pipeline. As you can see from the graph, the difference is around 12–15% for Clang 18 and 19, but with the release of the latest version, the difference, the speed up is 27%. So yeah, these results are quite impressive, but the question is it good for all workloads? And it turns out it is not. In practice, we found a 4% compile time regression for SQLite with Clang, which is optimized by Bolt. So there could be several reasons for that, and our hypothesis is that bolted Clang is trained on more than C++ code, and maybe it is not enough for SQLite because it is a C code base. So we were wondering, is it only one case with regression, or can we find more? And to check it, we decided to run CTMark benchmarks, and turned out that, yeah, we can find even more regressions. CTMark is a collection of applications for measure compile time performance, and more over half of these benchmarks are C code based. So you can see from this chart that all of C code-based benchmarks actually have a regression up to 6%. The results are shown for Clang 19 version. But yeah, we decided to extend our experiment for Clang 20, and we got a nice surprise here. Instead of regression, now we see a 20% improvement. The same is related to CTMark benchmarks. So yeah, no more regressions, only improvement up to 20% to C code-based benchmarks. And this is not what we expected initially when we started our work, but the question remains the same. Can we do even better than that? The significant improvements which we see on the latest Clang version could come from different sources. Maybe someone changed CMake configurations, maybe different options passed on, maybe Bolt learned new optimizations, or more and better profiles were added. So given all of that, our new hypothesis is that we can improve performance even more by extending the training stage. So the Bolt-optimized build currently uses only C++ code-based profiles, so maybe we can extend the training phase with a C code base, collect different profiles, merge them all together, and merge them with original profiles which are already present, and feed it into Bolt output to improve Clang even more. I used Bolt instrumentation to collect profiles for CTMark benchmarks, and as you can see from this graph, it actually helps for Clang 19 versions. So green charts here means comparison of Clang 19, like original stage 1 build, with bolted Clang 19 and gray line. Gray charts here means like bolted Clang 19 with extended profile. So regressions were fixed, and we can see up to 6% improvement. But when we go to Clang 20, the results are not so impressive. In average, we have only 1% improvement. Again, here, gray charts means like Clang 20 with extended profile. But yeah, let's also look how changed the time compilation of Clang building itself. So as you remember from the previous slides, this chart shows like timed LVM compilation for AArch64 Grace CPU in seconds. So blue line means standard build, orange means BOLT-optimized, and now we have a green line, which means BOLT-optimized Clang with extended profile. So for Clang 19 version, we have additional 6% improvement, but unfortunately we see no difference for Clang 20. So given all of that data, what conclusions can we make? The first one is that Clang 20 and Bolt 20 are great, and they're doing great on AArch64. Bolted Clang 20 is almost 30% faster compared to original Clang 20 stage 1 build. And it's also universally good. We have the same or better performance both for Clang build and CityMark build. And it also fixes the issues which we had on Clang 19 and older versions that were not great yet. And if you still have a question, should you bolt your Clang release? The answer is yes, you should. And as I'm aware, currently we started to do it upstream with the latest commit. And experiments with extending profiles also proved its efficiency. So the main difference in Clang 20 bolted performance is because it was currently trained on LLVM support, and this brings a big improvement. Currently, the percentage of functions which is covered with profile increased from 6% to 15%. So yeah, that's the main reason. Unfortunately, train it with more data, like benchmarks from CityMarks, almost makes no difference. And this brings us to the conclusion that the current CMake Clang Bolt build process and configuration is enough. In terms of future work, what else can be done? So firstly, CityMark apps are quite small, so probably it's worth to investigate more and bigger applications to cover more functions. And another option is that currently we use profile only on a bolt stage, so probably we can also use this profile to PGO stage to gather even more performance. Yeah, that's all. Thank you very much.